This is problem 17 from chapter 15 of the textbook Stats Modeling the World, and the authors are BVD. So here we're looking at drawing cards from a deck. We have to assume that the deck has been shuffled, and we're going to pick 3 cards. That's what makes this kind of a special probability problem. We're going to pick 3 cards, one at a time, and we're not going to put a card back. So there's no replacement. So what that means is the probabilities are going to change after each pick. So with a situation like this where you have a sequence of things, sometimes it helps to make a tree. So I'm going to use a probability tree to model the situations for these problems. So I'm going to go ahead and get started. I'm just going to draw. We're going to pick 3 cards. So I'm going to actually need 3 columns of branches, so to speak. Okay, I may not fill them all out. So let's look at the first question. The first heart you get is the 3rd card dealt. Okay, so let's say we get a heart. Okay, we'll use that notation, or no heart. Alright, so if we get a heart, or what's the probability of a heart? Well, there's, let's see, there's 13 hearts out of 52 cards. That means there's 39 non-hearts out of 52. Okay, so if we were going to model the whole tree, then we would say, okay, you get a heart, then you get another heart, no heart, and so on. But we're interested in the case where the first heart you get is the 3rd one. So we would go this way. We'd get no heart, and then we would get no heart again. Heart. And then finally we would get a heart. So we would go this route. So we're kind of looking at this event here. So let's see. Well, if we picked a card that was not a heart, then there would only be 38 left out of 51 because we picked a card, so it reduces. And there's still 13, right? There's still 13 out of 51 here. So there would still be 13 here, but there would only be 50 in the card, in the deck. 50 cards. So it gets reduced each time. So we would be looking at 39 out of 52 times 38 out of 51 times 13 out of 50. That's what this branch, the probability for this branch. So to write this properly, we would say the probability of the first heart is, hold on, H-E-A-R-T, the first heart on the 3rd card, something like that, is equal to 39 over 52 times 38 over 51 and 13 over 50. And that comes to, I think, 0.145 or 14.5% of the time. Okay, so that's how that's one way. Maybe you can think through it without the tree. So the tree is not absolutely necessary, but if you're like me, I oftentimes need a picture to understand what's going on. So let's try another one. Your cards are all red. So again, we're going to pick 3. So I'm just going to go ahead and fill out my tree. I may not fill all the probabilities, but I'm just going to say, okay, it looks like this, and then we're either going to get red or not red. Okay, and so your cards are all red, so we're just going to keep going this way. Red, and then red, not red, and then red again, not red. So we're interested in this branch. So there's 26 red cards. Half are red. So 26 out of 52, and then we pick another one, but there would only be 25 out of 51. And then there's, if we got two reds, then there would only be 24 out of 50. So the probability of all red is equal to 26 out of 52 times 25 out of 51 times 24 out of 50. Yeah, and I get 0.118 or 11.8%. Okay, so I didn't need to fill the whole tree out, but for me, it just works better if I think through things a little bit, draw a picture. Let's try C. You get no spades. Alright, let's try that. So again, we're picking 3 cards. Okay, so we're going to, let's say we get a spade or no spade. And then that just continues. Spade, no spade, spade, no spade, spade, no spade, and so on. But the one we're interested in, you get no spades. So that would be this branch here. Okay, so there's 13 spades, because that's a suit. 13 spades out of 52. So I believe this is 39 out of 52. So then if we pick one of those, then there would only be 38 out of 51. And then there would only be 37 out of 50. So the probability of no spades is equal to 39 divided by 52 times 38 divided by 51 times 37 divided by 50. And that should come to 0.414 if I did it right. So 41.4% of the time if you're picking 3 cards and they were shuffled properly and without replacement. Alright, so one more. Let's take a look at this. This one has a little bit more trickier situation, so I want to take some time to explain it. But when you get this language, at least for me, I have to slow down and think through what's going on. Just takes a little bit of thought. So first I'm going to draw the tree. There's 3 columns because we're picking 3 cards. Okay, so at least one ace. So we're either going to get an ace or no ace. Ace, no ace, 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 ace, no ace. Okay, so let's look at this. If this branch says that we get an ace, and an ace. This branch says we get an ace, and no ace. This branch says we get an ace, no ace, and an ace. And this branch says we get an ace, no ace, no ace. And this branch we get no ace, ace, ace. And this branch we get no ace, ace, and no ace. And then we get no ace, no ace, and an ace. And finally, no ace, no ace, no ace. Now with this picture, let's go back and look. You have at least one ace. So let's go through. Okay, so there's 3, 2, 1, 1, 2, 1, 1. This is the only one that doesn't have an ace. So one way to do this is that you would take this probability, whatever it is here, times this here, times this here, and you would get a probability for this branch. Then you would add it, and you would have to multiply this times this probability, and get another one. And so on. Maybe you can see where I'm heading with this. This is a lot of work. Okay, it's correct, but it's a lot of work. If it was a test, you're going to take up a lot of time. But you would have to, whatever these probabilities are, you'd have to add them all up. Or what you could say is the probability of at least one ace is equal to 1 minus the probability of no ace. Maybe I should say for all 3 cards. In other words, if you found all these probabilities for all these branches and you added them up, it would come to 1.00. So what you could do is just find this probability here and subtract it from 1, and that will give you all of these. Okay, that's called the complement. So let's do that. What's the probability of no ace? So there's 4 aces, right? There's 4 aces, so this would be 4 out of 52. So this would be, so there's 48 non-aces out of 52 to start. If we got one of those, then this would be 47 out of 51, and then this would be 46 out of 50. Right? So 1 minus 48 out of 52 times 47 out of 51 times 46 out of 50. Okay, so I would just punch that into the calculator, and you get, I got 0.217, or 21.7% of the time. Okay, so that took a lot, but I know that this, for some students, this is complicated until you do a few. So I think I relate this to like tying shoes. Every time you get one of these, if you take the time initially to draw this out and think through it, after a while you won't need to draw it out and think through it. But if you just kind of force your way through it and don't really understand it, then it may never be easy. It just depends. So I strongly recommend that you use a tree to model these kinds of situations. Even if a tree doesn't work, at least try the tree first, and then maybe it won't work. Then go to a Venn diagram or a table. Usually one of the 3 is going to be okay. All right, good luck with that.